In this online lecture, we're going to discuss the second aspect of NMR, and that is proximity to an electronegative atom and/or a multiple bond causes a peak to be shifted downfield. We want to understand this, why this is so, and use it to predict where peaks might be on an NMR spectrum. So let's look at an example first here. Let's say you have this molecule right here, and we put him into the NMR. And more specifically, we're going to put him into the HNMR, so we want to see the different types of hydrogens. We already saw the first aspect of HNMR, that remember the number of hydrogens correspond to the number of signals in the HNMR, so we would expect to see these to be the A-type hydrogens, and we would expect these to be B-type hydrogens, which means so far this is what his HNMR would look like. If we have energy on the x-axis here, we would expect to see two separate peaks, one for each hydrogen. And remember, we mentioned before in a previous online lecture that the reason why we see two peaks is because each one represents the amount of energy necessary to bring the hydrogens into resonance, and since A and B are in different electronic environments, they would have different amounts of energies, therefore separate peaks. However, it's not really that energy is on the x-axis of NMR spectra. What we're going to learn later on is that there's many types of NMRs that operate at different frequencies. So what they've come up here is more of a standardized X value here. So instead of energy, we're going to use what's called delta units or ppms, which stands for parts per million. Again, we're only using this unit because many NMRs operating at different frequencies can spit out the same data, which we'll make sense of more a little bit later. But for now, just know that the chart runs from 0 to usually 10 ppms, or delta units. And just like we saw before, the more further you're away from 0, or the closer you are to 10, you're more de-shielded. You're also more downfield. And the closer you are to 0, you're more shielded, or in other words, you're also an upfield peak. But here's something else we didn't mention in the introductory lecture. And that is, there's actually a peak right here at 0. And this is due to a specific molecule. That molecule is called TMS. We're going to see that TMS is our reference molecule whenever we're doing HNMR. To really understand HNMR, let's get a good look at this TMS molecule. Here's what he looks like this. And TMS simply stands for tetramethylsilane. Let's pay attention to the hydrogens in this molecule. First of all, notice all of them would be equivalent. So if we put him in the HNMR, we would only see one peak. However, let's look at his shielding. Let's say these electrons right here are surrounding that hydrogen. Do we expect the hydrogens for TMS to be shielded or de-shielded? Well, think about this here. Remember, carbon is not that much different from hydrogen in terms of electronegativity. And take my word for it, neither is silane. All of these atoms here in this molecule have roughly the same electronegativities, which means the green electrons around that hydrogen are going to stay right there, which means these hydrogens are going to be very shielded. In fact, what we're seeing in organic chemistry, these are going to be the most shielded hydrogens. So think about that. If TMS has the most shielded hydrogens, then again, let's go back to our chart here. Any peak that's, let's say, closer to TMS than others should have a similar environment. That is, they should be more shielded. Take this back to the principles too. Remember, a peak on the NMR gives us an idea of the energy necessary to bring a hydrogen into resonance. If you peak near TMS, then the amount of energy needed to bring you into resonance is pretty close to the energy of the hydrogens in TMS. And remember, if the energies are similar, it also means your electronic environment is similar. So that's why the hydrogens in TMS act as a reference of the most shielded. And using the same logic, if you peak further away from TMS, the more you're not like the hydrogens in TMS, and the more de-shielded you are. Also, please keep this in mind. In a previous online lecture, we were doing sample problems which involved predicting the number of signals we would see in the HNMR for various molecules. When you answer questions like this, you don't include TMS. So for instance, the spectrum in front of you we would say we would expect to see 2 signals in the HNMR. Remember, the peak for TMS is going to be in all of our spectrums from now on, so that's why we don't include him typically in the count. So let's look at a sample problem and apply our knowledge here. Look at sample problem 1. It's saying provide a rough sketch of the HNMR spectrum of the following molecule. So in order to do this, we're going to use the first 2 aspects of HNMR. The first thing we should notice is this very electronegative NO2 group here, which means this would be an A-type hydrogen. They're the closest to the NO2 group. These would be our B-type hydrogens, and right here would be the C-type hydrogens. So far in our sketch here, we would expect to see 3 peaks in the HNMR. And there it is, the first aspect of HNMR. But the second aspect here is assigning each one of these peaks to the specific hydrogen. And remember, the aspect simply states that the closer you are to an electronegative atom and or a double bond, the more shifted you're going to be, or we can say the less likely you'll be like TMS. So the most shifted peak should be due to the A hydrogen. The second shifted peak should be B, and the least shifted peak should be C right here. So this is what we're learning, how to determine the relative shifts of hydrogen in a given molecule. Let's look at another example here. Again, let's provide the rough sketch. And let's start out by pointing out that we have an oxygen right here, and let's label this hydrogen right here as A. Remember this principle, that means that this would be an A-type hydrogen, and these would be A-type hydrogens. Remember, due to signal averaging, which only leaves these hydrogens over here, they must be the B-type hydrogens. So in our rough sketch right here, we should expect to see 2 signals in the HNMR. Just a side note here, you might be wondering, why are we getting different heights for these peaks? We're actually going to specifically study this when we look at the third aspect of HNMR. So don't worry about this just yet. So which one of these hydrogens would be more shifted? Well, notice the B hydrogens right here should be closer to the oxygen. If we count our steps here, they're 1, 2 units away. Whereas all the A hydrogens are 1, 2, 3 units away. So that means the most shifted hydrogen should be B, and this should be the signal due to the A hydrogens. Let's look at another example here. Again, provide a rough sketch. Let's start right here and call these the A-type hydrogens. We see symmetry, so these would also be the A-type hydrogens. This would be a B-type hydrogen right here. The CH2 would give rise to C-type hydrogens, and the methyls here, they'll be D-type hydrogens. So in our rough sketch, we should expect to see 4 peaks in the HNMR for this molecule. However, notice here, there's no electronegative atoms or multiple bonds. However, there's an important principle you should know here. When it comes to shifting, we should always stick to this rule. Tertiary hydrogens are more shifted than secondary, which are more shifted than primary. We should know this at our fingertips. We should also know why, but we'll talk about that in a few minutes. Let's just apply what we just learned to this spectra. Notice, if you look at your molecule, it's the B hydrogen that happens to be a tertiary hydrogen, so he would be the most shifted peak. Then notice the C hydrogens are secondary hydrogens, so they should be second most shifted. And notice the A and D hydrogens are both primary hydrogens, so these last 2 peaks over here should be A and D. They would peak roughly near each other, and it doesn't matter if we know which one would be more shifted than the other. It's good enough for now just to know that they would be peaking near each other on the spectrum. Now, why do we observe this shifting trend? Well, let me show you an example here. Let's say we have 2 hydrogens here. Notice this hydrogen on the left here happens to be a tertiary hydrogen, and this hydrogen on the right over here happens to be a primary hydrogen. Now remember, carbon and hydrogen roughly have the same electronegativity, but carbon is slightly more electronegative than hydrogen, which means the tertiary hydrogen would technically be in the proximity of 4 carbons, whereas the primary hydrogen is in proximity to 2 hydrogens and 2 carbons. Since the tertiary hydrogen is surrounded by more carbons, and remember carbons being more slightly electronegative than hydrogen, then that's why the tertiary hydrogen will be more deshielded than the primary hydrogen. and will therefore peak more downfield. So this is why we observe this particular trend right here. In fact, let me share with you the actual ppms. The A and D hydrogens would peak probably around 0.85 ppms, the C hydrogens would peak at 1.2 ppms, and the B hydrogens would peak at 1.5. Notice these shiftings are not drastically different. Remember, the chart goes from 0 to 10, so if we looked at a zoomed out view, all four of these peaks would be bunched together near in less than 1 ppm. However, remember our NMR is a very sensitive machine and is sensitive enough to resolve all four of these peaks. Let's look at another example here. One little skill I want to mention here, if you're on an orgo exam and they're asking you for the rough sketch of this molecule, remember, since it has a double bond, it's safe to start out by redrawing it in this format. Remember, this helps us see the geometry better, which in turn helps us know the environments of the hydrogens better. And remember, the HNMR is all about different environments. So let's start somewhere and label a hydrogen. Let's call this guy the A hydrogen. That would make this one the B hydrogen, and that would make this one the C hydrogen. Remember, we saw in a previous online lecture that double bonds do not rotate, so this is why all these hydrogens are different. And lastly here we have the D-type hydrogen, which means a rough sketch of this molecule would have 4 signals in his HNMR. Now remember, not only electronegative atoms cause your peak to be shifted, but also multiple bonds. In this particular example, we have a carbon double bond, so any hydrogens closest to that double bond will have more shifting. We'll go into why this is so a little bit later. But we can at this point assign the hydrogens to the given signals. Notice at first glance you might think the A, B, and C hydrogens are equal distance to the double bond. And in fact they are. So for this molecule, the C hydrogen is going to be the most shifted. Why is that? Well, remember, the C hydrogen is a secondary hydrogen. And both the A and B hydrogens are just primary hydrogens. So even though A, B, and C are the same distance from the double bond, since C is secondary, he should be the most shifted. That leaves the next 2 peaks here due to A and B hydrogens. In this example, we would expect to see the A hydrogen to be a little bit more shifted than the B because the A hydrogens are closer to the methyl across the double bond from him. Again, remember, carbon is slightly more electronegative than hydrogen. And obviously the last peak, the only one that's left, this must be due to the D hydrogens. And just to give you a rough idea of values here, the C hydrogen would actually peak at around 5.5 ppms. This is just to give you an idea of how powerful the shifting effect is due to double bonds. Notice this C hydrogen would peak almost halfway down the chart. The A and B hydrogens would peak at around 4.5, and the D hydrogens would peak at about 1.7.